Hello, everyone. So thank you, John, for the overview, and to the organizer for organizing this and letting me speak today. Thank you. So my name is Andrea Rizzi. I'm a grad student in Codero Lab. I started around 3-4 years ago, and I've been helping out with the sample challenge this edition by performing the reference calculations and the analysis of the submission for the host guest challenge and the sampling challenge. I'm going to talk about the main host guest challenge right now. I'll have a separate talk for the sampling challenge later. So first I want to spend a couple of words about why it is valuable to study host guest systems. And I'm going to draw a parallel with what I was doing like a few years ago. I was testing algorithms to predict vehicle collisions and possibly to avoid them. And in this case, it's fairly intuitive that it's ideal to test these algorithms on controlled systems that before actually buying an expensive card and testing on them. So we will not fail. If our methodology fails, we want to know it very quickly and very fast. And when moving to molecular system, the parallel is very similar. Protein systems are very expensive to simulate, and if we want to run challenges and compare many different methods or many different systems to have the statistical power to make conclusions, we need to have something that can fail fast. And host guest systems are perfect for this. They have a much smaller much less conformational degrees of freedom. They are smaller than protein in general, but also they have a chemical state that is usually simpler. For protein, the protonation state, there can be multiple protonation states that can affect binding process, while for host guest system, they have less protonation states available, and also they have the advantage that experiments can be done at pH that are very far from physiological pH, and so we can actually move the equilibrium towards more unambiguous pH states. But at the same time, on the other hand, host guest systems use the same physics of binding of proteins. They can bind a small molecule with a high affinity, which is very important since some of these methodologies have fallacies when it comes to weak binders. So in this challenge, we have 3 hosts and 22 guests. 8 of them are shared between 2 different hosts. So we have a total of 30 host guest systems. So I'll talk a little bit about the systems that are involved in this challenge, and just to give you an idea about what kind of challenges this chemical host poses. And then I'll give a very quick overview about the experimental measurements and the results. So these are the first two hosts. Obviously, they are within the same family. They were developed in the lab of Bruce Gibb at Tulane University, hence the name of the family. The only difference between the two are these 4 methyl groups that appear here at the entrance of the binding pocket. The ligand enters this basket-shaped binding site. And this is the third host that we have. This is from the family of cucurbiturials. This family was used as well as the octaacids in previous sample challenges as well, or derivatives, or a member of the same family. One of the key aspects of this is the top-bottom symmetry, which open up the possibility of flipped binding modes. Typically, this means that when sampling the conformational space, either we need to use some kind of accelerated sampling to be able to flip and sample all the relevant binding modes available, or we need to make sure that we don't flip and we correct for symmetry later. Another key aspect of this is the portal, which is relatively large and open up the possibility for different binding stoichiometries, and I'll talk about it a little bit later. And both families have somewhat shared challenges. One of them is water binding and unbinding. So for both the cucurbiturials and the octa acids, water binding and unbinding was found to actually affect correlation rates. In cucurbiturials, they have been found large fluctuations of the binding site wetting and unwetting. And for octa acids, it has been found slow in and out movement of water on the order of 5-10 nanoseconds. Secondly, both experiments or calculations are actually sensitive to the ionic strength. So extra care must be taken when modeling the buffer conditions for the comparison to make sense. This is the first set of guests. Both of them bind both octa acid and tetramethyl octa acid. They are all small and fragment-like with a charged end, and this reflects the typical binding mode of these compounds that have a polar or charged end that face and interacts with the solvent, and a hydrophobic part that is stick inside the basket. All of these experiments have been performed at a pH of 11.7. So these ligands tend to be charged. On top of this, the octa acids actually have 8 carboxyl groups. And I predicted with EPIC the most likely conformation state, and it turned out to be fully deprotonated. I don't actually know what is the free energy moving from the first one to the second likely. I think all of the participants used the most likely protonation state, which means that the box is very highly charged. Typically, in explicit solvent simulation, at least, you need to out-counter ions, and we have 8 charges for the host alone, plus 1 charge to correct for the ligand, plus simulating buffers concentration. So there are a lot of separate charges in the box to simulate for this set of systems. In the second one, cucurbiturials don't have acidic or basic group, and the experiment were done at pH 7.4. Again, all the participants used the most likely protonation state for both the hosts and the guests. These guests have a lot of amino groups whose most likely protonation state is protonated. So, but usually the charges in these systems are relatively few. These set of ligands are a little bit more diverse. They are more bulky, more drug-like. 3 of them have been designed, the one that are framed in magenta, as bonus challenges. And the reason is oxaliplatin here has a platinum atom here, and well, common force field are not terribly well equipped to deal with these kind of atoms. And the second one, according to the first results of the binding stoichiometry, these 2 have been found to bind in 1-2 complexes. And so they are a little bit atypical. Actually, these turned out to be 1-to-1 in the end. I'll talk about it a little bit later. So all the experimental measurements were performed in Bruscape group and in Lyle Isaac's group at University of Maryland. Stephen Merkley and Nolan McNeil were the grad students that performed the experiments in Isaac's group. The experiments were performed using ITC, and the dynamic range of the single set of octa acid and CB8 is actually on the order of 4 kilocalories per mole, but the overall range is about -6, -10 kilocalories per mole. This is relatively important when we look at statistics like correlations, since if the dynamic range is too small, we are just basically feeding error. So in the analysis, we have provided statistics for single sets and also overall sets. Binding stoichiometry were determined by proton NMR. For the octa acid set, all of them turned out to be 1-1 complexes, but we had few exceptions for the cucurbiturials guests. So I told you about the bonus challenges. Aricept here can bind to 1-2 complexes. This guest was actually, there was a small error in the calibration of the solution of CB8, and so after a second measurement, it turned out to be a 1-1 complex. the participants have not been affected too much by this, as all of them submitted calculations for a one-to-one complex for both of them, as far as I could get out of the method section. But there was one group actually that tested this hypothesis and for both of them, and blindly predicted that the second compound would not bind, which I thought was pretty cool. And then we have these other atypical binders, which actually binds galamine triethiodeate, for example, binds 3 hosts to 1 guest. From the isotherm of the ITC, from the symmetry of the isotherm of the ITC, it looks like these 3 binding events are approximately equivalent. So we were able to provide free energy calculations for both of them for a one-to-one complex. So I'm going to give you a very quick overview of the results. I'm not going to get into the details. We're going to have talks and posters later. But all the analysis is available online. Nobody chose to submit anonymous predictions, which I thought was fantastic. The analysis is going to be a work in progress until the paper probably, but you can verify correlation plots and bootstrap statistics grouped by methods or molecules. And all the submissions have been uploaded there, so you can actually go into the method section and see what the participant did. We had a lot of participation, 87 submissions for the octa acids and 34 for CB8, for a total of 9 participants. Half of the methods came from Lin Sang. He was very generous. He tested a lot of different variation of his algorithms. So in general, the octa acids were a little bit more preferred than CB8. But we also had few submissions for the bonus challenges. That was interesting. So I tried to come up with a classification of the methods. We have a total of 47 different strategies. It turns out that there are so many variations that it's very hard to make a single classification that makes perfect sense. But the main point of the slide is that there is a lot of great data up there. A lot of different methods have been applied. Equilibrium chemical calculations, non-equilibrium, relative or absolute. I think these relative, if I remember correctly, there are relative calculations using only molecular mechanical models or molecular mechanical models as reference potential and compute the free energy of moving to a QMMM potential. We've been having QM submissions, umbrella sampling. A couple of groups also used previous experimental data from sample 5 of the literature, trying to come up with fitting a linear correction to improve the results. I thought it was interesting too. I also took a look transversally across methods, trying to identify possible outliers for the molecules that we can have problems with. I couldn't find much here. The general trend is, as I expect, the smaller fragment line molecules that binds the octa acids perform slightly better than CB8 and to be with a smaller error, but the bootstrap confidence interval are so large here that there is not much that we can say with statistical significance. Probably the only thing that we can say is that well, here at the bottom there are the 2 real bonus challenges. G13 is the one with the platinum atom, and G12 is the one that has a 1-to-2 binding stoichiometry. And these methods seems to perform, these molecules seems to be predicted statistically worse than a lot of these other molecules right here. Most of them, as I told you, submitted prediction for 1-to-1 binding stoichiometry, but this is probably symptomatic of the fact that we don't really know how to deal with this in a standard way. And these are the overall statistics. So we just had a discussion session trying to figure out metrics that predicted. So this is just RMSE. I encourage you to go and take a look at all the statistics there and draw your own conclusion. But the best method performed with a RMSE of 1.74 kilocal per mole. Here, the null method here is a very simple, just assign 0 to everything. And we are having 2 talks and 3 posters today, and are going to talk about what worked, what didn't work. So I encourage you to check them out if you can. And with this, I just want to acknowledge everybody, first of all the participants and the D3R and Sample 6 organizers, in particular David Mobley, Michael Schurtz, Michael Chu, and Michael Gilson. All the people that performed the experiments and the grad students that performed them, and people in the Codero lab, Metaphysic, Bas, and Levi, and the Tri-I Computational Biology PhD program, who is partially funding me. Thank you.
We have a few minutes for questions. Well, I have one. With all the warning about the importance of the charge state and the ionic strength, what was the ionic strength that was used for the ITC experiments on the host guest systems?
So the pH was relatively high, but the truth is we don't really know, because we don't have an estimate of what is the free energy of going from one ionic state to the other.
But what I mean is the ionic strength of the buffer.
Oh, sorry. Okay, sorry. It was in the range of 20 millimolar. The ionic strength. Oh, yeah, I remember this. It was 58 millimolar for the CB8 solution, and around 40 millimolar for the octacids.
These phosphate buffers?
It was phosphate buffers. Yeah.
And the solutions were always just water yes. With phosphate buffer. Excellent. Okay. Any questions? John.
I don't think we've taken this apart yet, but I'm particularly interested in how the RMSE errors compare to the D3R RMSE errors, to see if there's something intrinsically harder about these host systems than we seem to be doing for the prediction of affinities for protein ligand. Do you have any idea after this one session how that works?
Sorry, I'll be calling you.
Not really, actually. I don't know. Yeah, that's an interesting question.
Dude.
So the ITC can also be analyzed with enthalpy. Did anyone was enthalpy involved in the challenge enough?
Yeah, we had 3 submissions for the enthalpy for octacid gas, and I think 3 submissions for the enthalpies of the CB8. The statistics were not very good for those. I have the correlation plots and the statistics online, and I can share them with you. Yeah. But the enthalpy prediction was harder, it seemed.
David.
To look at this, maybe you didn't either, but superficially, we had the impression that maybe because of past experience with octacid, it might have been a somewhat less challenging challenge for people than CB8. Do you comment on whether that's the case?
I think so. So one of the things that stick to my eyes is that the methods that performed the best were the ones that used a linear correction to the free energy fitted on previous sample data, which is very reasonable to do, but you need the right data to fit the parameters, and that correction moved to a different set may not work as well. So yeah.
So for the experimental side, some of the gas molecules for CB8 is overlapping for sample 4 for C7 host molecule, but those experimental values are quite different. I remember like 4 or 5 gas molecules exactly the same as the sample 4 for sample CD7. So why don't we try to the multiple experiment for using different gas and also get some statistics?
Sorry, can you repeat?
So maybe we can do some multiple experiments using different methods, finding affinities, that we can get some reasonable statistics.
You're worried that this, because the same ligands bind CB7 and CB8 values are very different, there might be a problem with the experiments. Yeah. It has been done before that people have done very careful studies at the same time of CD7 versus CD8 binding is very different. CD8 is significantly bigger.
Right. I'm still thinking of the better way to get the reference.
Yeah. So as I'm not an experimentalist, I so take this with a grain of salt. But for what I could see is this year the experiments were performed only with a single replicate. Last year, at least, there were 2 replicates, and the ITC experiments were agreeing very well to each other. This year, we have estimated errors, model errors that were within model concentrations error, assumed them to be around 3%, and we propagated the errors of the feeding procedure. The error bars were actually showed in the slide that I showed you, but they were too small to be visible. So it could be a possibility, but I will tend to trust those ITC measurements, also because I think this group has performed a lot of measurements with this system, so they are definitely aware of the challenges that lies underneath. But that's definitely a possibility.